Okay, so this lesson is really 2 or 3 different sections that I have to get through at a time. The first one I want to start with is talking about how most of the time when we work with trig, we normally work with small acute angles, things that are less than 90 degrees. And because of that, we can plot them. If we wanted to plot them like on a grid, we can plot them in quadrant 1. Does that make sense? So, I mean, if I were to plot any sort of triangle, so long as the angle isn't like 115 degrees, 45 degrees, that could be 1, 2, something like that. It normally fits in quadrant 1. But it doesn't have to. What if our angle increased to the point where it was something in this quadrant here, where if I were to make a triangle out of it, there was like a triangle, like an obtuse triangle sitting over there. And by extension, could I not kind of continue the angle increase all the way past 180 to the point where really this triangle is now like upside down in like the bottom half of the quadrant hemisphere, right? Where this angle is on the outside is 225, or even like all the way around, almost to the point where you've done a full 360, and you've kind of made yourself like, say, a triangle in there. So part 1 of my lesson here is to talk about, well, what would that look like if we placed them in different quadrants? Does that make sense? So before I get to that, I need to make sure you guys are up on the terminology. Do you guys know complementary and supplementary angles?
No.
Okay. I promise you know how to do them, you just don't know the words then. If I were to tell you that this angle right here was 30 degrees, that one's 60. Because they add to 90. Right? Any right angle that gets split into 2 pieces, it adds up to 90. And if you had a straight line, let's say that this was 115 degrees, this would be 65 degrees. Those are called supplementary angles because these guys add up to 180. Does that make sense? I promise you, you know how to do the math. You just didn't know the words for them, that's all. Other terminology before we start an example here. If we're going to place an angle like on a grid, in terms of definitions, we call this standard position. I don't know, standard. It's the general way that everybody does things. Where you always put like this point right here, the vertex of your triangle, you put it at the origin. And then you call this side the initial side, or like the initial arm. This side over here is the terminal side. And you can really have this go anywhere. Like the picture I just showed you there, you could have this end up in quadrant 1, quadrant 2, quadrant 3, quadrant 4. You just you keep rotating it. Kind of like how a clock rotates, I guess, only a clock goes clockwise. This is going counterclockwise. That same sort of thing, right? Like as the angle increases, you get to 90, we'll keep going past 90, even down into the lower quadrants, and then kind of come back again. You can visualize what I'm saying here. So here's another picture kind of talking about the same stuff. We're now going to start putting angles in different locations where this angle right here might end up being 110 degrees. One of the key properties is what's called a reference angle. You guys talked about this a little bit yesterday? Okay, let me try to do a better job of describing the word reference angle. Okay. A standard position angle is basically starting here at 0 and figure out how wide you open your angle. That's called a standard position angle. Whereas a reference angle is the angle, the shortest one that you can make that goes to the x-axis. It's always to the x-axis. You see how like here you're going all the way around the circle? This angle right here would be called a standard position angle, starting at 0 and opening up over and over and over again. The reference angle is then the smallest angle you could make to the axis again. So you guys see how you can kind of make like a little triangle inside here? It's kind of like whatever Pac-Man eats, if that makes sense. All the way around here is Miss Pac-Man. The reference angle would be like a little leftover triangle. So that's our terminology. Standard position, start at 0, start opening the alligator mouth as far as you can, even past 360, even past 180. The reference angle could be the last little bit left over. So in quadrant 1 then, your reference angle is your standard position angle, by the way. There's nothing special here. In quadrant 2, you get like a little triangle kind of kicking around over here. In quadrant 3, you get a little triangle kicking around right here. which is, this is 180 degrees. So then this is like a little bit more than 180. Quadrant 4, it's like the Pac-Man example where the whole thing would have been 360, except you're kind of peeling off whatever's left over. That makes sense? I'm getting a lot of nods here. So far, this is really just terminology, just so that you know what the words we're going to use are. So let's try some examples. It's real basic. I need you to tell me the reference angle for each of these standard position angles. So here's the first thing I do. Let's plot it on a graph. Make it just a very generic XY plane. Don't use a ruler, I could care less. 0 degrees is defined as like due east. I don't actually know why we picked 0 for east, but that's just where it started, I guess. If you were to open up this angle till you got to 150, it would look something like that. Where right there, that would be your standard position angle of 150. So far, so good? Anyone tell me what the reference angle is going to be? 30, yeah. Because what you really have is a triangle right here, where the leftover little bit is 30 degrees. So definitions-wise, we would say 30 degrees is your reference angle. All we're doing is we're opening these triangles up now to being more than acute triangles. We have to talk about what happens if they're obtuse triangles. What if they are so obtuse that they open more than 180 degrees? Sometimes opening more than 180 doesn't make sense to a lot of people, because like say a door. The most a door could most of the time open would be 180, because you could swing the thing all the way open and it would like hit the wall on the other side there. But I mean, what if the door was on some sort of pivot and it could actually go further than that? You know what I'm saying? Like there are some hinges that open more than 90, open more than 180. They can go almost all the way around in a circle. So we have to have a way of accounting for that. Let's try a second one. If I asked you to plot a 60-degree angle, 60 degrees would just be sitting right here in quadrant 1. There's really nothing special to it because 60 degrees is both your standard position angle and it is the smallest reference angle you can make as well. Because like the smallest triangle you can make is the one you just made. There's not like some extra triangle. Whereas 240 degrees, this is on some sort of hinge that can rotate past 180, right? So you started here, you started rotating, you kept going past 180. Where's 240 going to be? Right about here? Does that make sense why I stopped right about here for 240? What would this line right here be? You guys know? Straight down? Okay, you guys are good on that? This would be 0, 90, 180, 270, and then all the way back to 360. Okay, definitions-wise, the reference angle then is the triangle you make with the x-axis, not the y-axis. So it's not this triangle right here because that I'm drawing to the y-axis. We've defined it. We just had to choose one. We just said x. So you have to make the triangle go back to the x-axis. So if all the way around to here is 240 degrees, that would be your standard position angle. How much further past 180 did you go? How much is this extra little bit? How much further is 240 from like stopping here at 180? 60, yeah, you'd say 60 degrees is your reference angle. The reason why we need to have a reference angle is that most of the trigonometry we're comfortable doing is based on acute angle triangles. Like we're comfortable working with less than 90s. Does that make sense? As soon as we start opening things up past 90 degrees, even past 180 degrees, we can still do that. But it's usually easiest to do it if we think of them as like there is a smaller acute triangle somewhere hidden inside there. Right? So what we use is we use the hidden triangle to try to solve the larger one. Okay on this? Okay, let's do an example. This guy here is doing leg extensions. You guys kind of get the machine he's on here where he's like sitting like this, and he's going to lift his legs up like this, do extensions. You can kind of visualize that. And I suggested that I can see an angle in there of 240 degrees. Because starting from his legs right here, all the way around like that, it's 240 degrees. Can you kind of visualize that? Right? That's the angle that he's created based on where he's sitting. Hello. Can you call the other math classroom? Which is it's the one that Ashton uses. That's where the dash 2s are. Okay. So far so good. So if I were to kind of plot this out a little bit here. This thing just randomly stops working. Come on. Come on. There, okay. So if I were to kind of plot this on a grid here, the guy is like, I don't know, upper thighs are right here, his shins are going down here, and the angle all the way around is 240 degrees. Does that make sense so far? If I were to try to solve for this though, here's some other information I have here. His feet, if his knees are bent all the way down, his feet would be 5 inches off the floor. Okay. His feet would be 5 inches off the floor. So like, let's say that this was all the way down like that. There'd be like 5 more inches further down to the floor. You guys kind of visualize that?
Isn't the 5 inches when his knees are behind him?
Says he sits it so that when his knees are bent at a right angle, his feet are 5 inches off the floor. So let's say that his feet swung all the way down here to the bottom. That was it. Okay. Am I interpreting this the same way you guys are? If his knees were bent all the way down like this, if this is where his knees would be, then he'd be 5 inches off the floor. Does that make sense? The other information we get is that the height of the chair is 34 inches above the ground. So if this is where the chair is at, from here to here is 34 inches. What does that information help me figure out? Not so much the triangle yet. It helps me figure out how long his legs are. Okay, because if from here to here is like the length of his, like, say his leg, like his shins, does that make sense? From here to here is 34. From here to here is 5. That's 29. You guys see that? From the chair to the floor was 34. But he was 5 inches above the ground. So if I subtract those two, it says that his legs, like from here to here, that's 29. Now it's 29 regardless of how he swings his legs. You'll visualize that? So what I'm really telling you is that this right here is 29. It's 29 from here to here, but it's also 29 right there as well. So although this is a very confusing setup, we're going to use this basic right angle trigonometry to solve this. What we have in here is a reference angle then that looks like this. This is 29 inches. Now, if all the way around was 240, you guys remember how we just said that that was going to be like 60 degrees left over? I should be able to solve for x and or y, depending on whichever one actually matters to me. So I can just use basic 90-degree trigonometry to find x or y. And I think what it wants is determine exactly how far his feet are above the ground at this point right here. So I'm just going to solve for his y value there. Based on this triangle right here, to solve for y, I would use sine. I'd say sine of 60 degrees would be the opposite over the hypotenuse. I'd swing that up there.
But for that, isn't the top one also 29? X?
No, it would be 29 all the way over to like, if this were to keep swinging, 29 would be like if his legs were completely out. From here to here would be 29. You know what I'm saying here?
No.
Here's his legs right here. You can see that. Here's his legs at like this angle there.
Okay.
And then here's where they would be if he was like, if you were sitting like this, okay, where his legs are completely flat out. But in terms of the reference triangle that I'm drawing, that triangle is only that far. So I know this is 29, that's 29, this is 29, that's 29, but I actually don't know how far it is just to there. That's good. Alright, so the hypotenuse is 29. We don't know the x or the y distance. I'll find the y distance, 29 sine 60. Now, you could go to your calculator and try typing in 29 sine 60, and it'll give you some decimal value. One of the things I wanted you guys to practice was, can you avoid writing sine 60 and replace it with something else instead? You guys have one of those charts nearby that tells you what the equivalence of sine 60 is? You guys know what I'm talking about here from our lesson the other day? That'll work. So call this 29 root 3 over 2. That's what y is equal to. That's now, I'm using my fingers here, but that's now an exact value because it's a non-rounded value. Did I lose you guys on that step, or are you okay?
No, I didn't hear it.
Okay, and you weren't here when we did exact values. So Jake, this is what you're going to want to watch here, is that for certain values, rather than writing sine 60, and like say going to your calculator and saying, what is 29 sine 60, and getting a decimal number, it's better to know the equivalency. And we learned the other day that sine of 60 is equal to root 3 over 2. So rather than writing sine 60, we just write root 3 over 2 in its place.
What about the sine of 59?
It's only doable for 30, 45, and 60. Those are the only ones that we have exact values programmed for. Otherwise, we do have to round at some point, or do our best. So. Alright, so anyways, y is now 29 root 3 over 2. So that means that this side length right here is whatever 29 root 3 over 2 is, which looks like it's about 25. My question is, how high are his feet above the ground at this point? So I'm actually asking you for how high that is. I'm expecting it to be slightly more than 5. Because at the very, very lowest point, it was 5 inches. Now that he's swung his feet up just a little bit, it should be a little bit more than 5 inches, right? So to get the right answer, you know how the total distance right here was 34? As an exact value, your answer would be 34 minus 29 root 3 over 2. That would be your exact distance. As an unrounded value. That makes sense? Yeah? Alright, let's try another one. Okay, second example. There's one like this on your assignment even. You got a metronome that's going to tick back and forth in order to keep time when you play piano. It's going to move from 45 to 135. If I were to plot that out and kind of make like a, let's use a better color here. If I were to kind of make a grid out of it, can you kind of see how there's like 45 degrees sitting right here? If it went to 135 degrees, all the way around to there, how much is left over? If like 135 is your other angle, how much is this leftover bit? 45 again. Sorry, does that make sense? I'm asking for the reference angle. If 135 goes to here, it means that there's like 45 degrees left here. So, I mean, Rebecca, I think you're a step ahead of me because that's going to be my next question. If you start at 45 degrees over here and you end at 45 degrees over here, how much of an angle did it actually travel through? 90 degrees. Right, because 45 and 45, the leftover bit would be 90. Well, I'm asking you what the exact horizontal distance across is going to be. Here's one option. You can use Pythagoras' theorem. The metronome was 10 centimeters. So it's 10 centimeters on both of these sides right here. So use Pythagoras' theorem. 10 squared plus 10 squared equals c squared. 10 squared and 10 squared will give you 200. But I don't want you to give me the square root value of 200. We want to try to leave it in an exact value. So the best way of doing that would be to say it's root 200. 200 breaks up into, like, say, 100 by 2. So you can take 10 root 2. That's the exact value. You okay on that one? Okay. I said this in my grade 10 class earlier today. I guess I can share the same thoughts with you guys. Trigonometry, in my opinion, this is just me. Some kids, they find it brutally difficult. And some kids, they find it way too easy. And I think the thing about trigonometry is that there's very little work sometimes. Most of it's about how you interpret the question. If you can see the angles in your head and go, that's an opposite, that's an adjacent, there's your answer. Most of it just kind of can get done in your head, or like there's very little work. To me, honestly, the more important thing is that you draw the picture correctly and that you can set it up. Where if you know all the terminology, things like opposite, adjacent, hypotenuse, acute, obtuse, reference angle, standard position, as long as you know all the vocabulary properly, the actual work to it, sometimes there hardly is any work to it, actually. You know what I'm saying there? Some kids, they hate that, though, because they have no idea where to start, and they're just like, because it's frustrating, or there's nothing to it. Okay, so far so good? Okay, second half of my lesson. So second half here. You guys have learned about SOHCAHTOA at some point before, sine, cosine, tan. The truth is that we haven't told you yet the other three ratios, but there are actually three more. They are known as cosecant, secant, and cotan. But they're redundant. Did you guys know the word redundant? Unnecessary. Yeah, that'll work. There's actually not a lot of point to them. All that's different about them is that rather than going opposite over hypotenuse, you just flip it and you go hypotenuse over opposite. But why would you have 6 buttons on your calculator? Right? Because what you could have is you could have a cosecant -1 button, and then if you wrote it as hypotenuse over opposite and you inverse that, you could get an angle. But why would you need that when you already have a sine button? So basically the idea is if you wanted to, you could flip the fraction upside down. Not that there's much purpose to it, at least until next year when we talk about it more in grade 12. But I need you guys to know the extra trig ratios here. So I want to do some examples of these now. So sine, cosine, and tan are just like you've always learned them. Sine has a buddy. Sine's buddy is a cosecant, where rather than it being opposite and hypotenuse, it's now hypotenuse and opposite. Just flip the fraction upside down. That's called a reciprocal. Cosine has a buddy called secant, where rather than it being adjacent over hypotenuse, you could flip it upside down and make it hypotenuse over adjacent. There are some calculators that actually have a cosecant button on it. But do you guys get where I'm going here, where it's kind of pointless to have a cosecant button? Because you could just use the sine one instead. And then also tangent is normally opposite over adjacent. You could flip it upside down and make it adjacent over opposite and do a cotangent. Here's how I remember them. Every single pairing has the word co in one of them. Sine doesn't have the word co in it, so its buddy has to be the cosecant one. Cosine has the word co in it already, so its buddy is just secant. And then tan does not have the word co in it, so its buddy is cotan. That makes sense. So, anyways, long story short, this is going to seem stupid. It really will. I have my grade 11s ask me this all the time. Mr. Schultz, what is the point to this? And I have to tell them, right now there isn't any, and I find it so frustrating because this is like where we stop. And it's like, well, why can't we just keep going on to grade 12? So bear with me. If it sounds like this is a waste of time, it's because at least right now it kind of is. But we will work with this next year a ton. So anyways, more diagrams. Let's try an example here. When you guys were in grade 10, you probably learned how to write all of the trig ratios for something like this. If I gave you these sides to the triangle here, would you guys agree that you should be able to solve for this side right here using Pythagoras' theorem? Okay, let's try that. It would be 11 squared minus 4 squared, because this is the hypotenuse right here. And because this is where we're trying to lead to, let's try not to make it a rounded number. So 11 squared minus 4 squared gives you 105. Square root of 105. I don't see that being able to be reduced. But what I'd rather you guys do is don't call it like 10.1. Can we actually leave this as like root 105? That makes sense. Okay, so if you wanted to solve for, say, an angle, come on. If you wanted to solve for an angle right here, you could write this in a couple of ways. You could say that, say, the sine of theta would be equal to the opposite over the hypotenuse. That's one way you could write it. You could say that cosine of theta is equal to the adjacent over the hypotenuse. You could say that the tan of theta is equal to the opposite over the adjacent. And if you grabbed the graphing calculator and inversed any of these things and tried to solve for this angle here, shouldn't they all give you the exact same thing? Let's just prove it real quick. Inverse sine root 105 over 11, just to make it exact. This should be 68.6763 degrees. If I'd have used cosine, same thing. If I'd have used tangent, same thing. With me so far? Those are known as the primary trigonometric ratios, and because that's really all you need to get going, we abbreviated them SOHCAHTOA and teach them to you in grade 10. But a special, more advanced calculator might have a button for what's called a cosecant. We don't have a button for cosecant, but if we did and we wanted to solve it, the only difference is rather than it being 105 over 11, it would be 11 over root 105. That's all. And rather than having cosine be 4 over 11, its buddy is secant, it would be 11 over 4. And if we had a button for cotan, it would be 4 over root 105. Hypothetically, if we had a cotan button and we had an inverse cotan to go with it, it should give us the same angle. But hopefully you see where I'm going here. We don't need to worry about these ones here, because why bother doing one of these when you can just do one of these ones instead? So almost every calculator I've ever seen, they don't bother putting buttons on there for those ones. But you might find them somewhere. One more thought. Two of these ones actually need to be written a little bit differently. You guys know which ones I'm referring to? You need to rationalize. Rationalizing is not hard. If you know what you're doing, you have to times by root 105 over root 105, which means this one is actually 11 root 105 over 105. And this becomes 4 root 105 over 105. Like once you get the hang of it, take the square root off of the bottom, bring it to the top, and then write it again on the bottom, just without a square root. That's how you rationalize really quickly. You guys remember how to do that from our rationalizing unit? Anyways, I just want to show you the other three trig ratios. Again, if you're wondering, why is this useful for where we're going today? No, it's not. It really isn't. So, sorry. Okay, let's combine this now. The last part of my lesson then is to combine the two things I just showed you here. What if I were to give you these ratios for sine, cosine, and tangent, as well as cosecant, secant, and cotan, and let's put them onto a grid. How does that work then, putting them on a grid? Okay. Well, the first thing is that you have to make sure that you put them in what's called standard position. So for it to work in standard position, this side right here better be at the origin, like the vertex was at the origin. We always make our triangle drop down to the x-axis. Okay? It would not be correct to draw the triangle like this. Just convention, always go to the x-axis. We had to pick one or the other, so x was the answer, I guess. And one more thought here. You know how I solved for this angle right here? We usually don't put the angle up in this corner here, though. The proper location of the angle is right here, and it keeps opening counterclockwise around the circle. I want to try a couple of examples of how this looks. Come on. Okay, here's just some notes talking about what to do. We no longer label them as A, B, and C. You know how like we usually do C squared equals A squared plus B squared? When we get to grade 12, we start usually labeling with different letters. My board is giving me so much problems today. You haven't noticed. Okay. We normally label this side right here with the letter R, this side here with the letter Y, and this side with the letter X. I feel like X and Y are self-explanatory, because really they're the X and Y sides of your axis. Anybody want to hazard a guess as to what R stands for? Radius, yeah. Because you can consider that R to be a radius as this thing goes around. It's making a circle as though it's a radius. So that's usually why we call it an R for radius. So no longer is this side the opposite. No longer is this side the hypotenuse. And no longer is this side the adjacent. The further you get into trigonometry, we usually change the terminology to X, Y, and R. But for now, I'll try to do it in both sets of letters, because really they're just letters. Who cares what letters you use? So that's what I have on this side right here. Rather than saying that sine is opposite over hypotenuse then, sine is sometimes known as the y over the r. Cosine is the x over the r. Tan is the y over the x. And then similarly for the reciprocal functions as well. X. In terms of reasons why, it fits better on a grid because this location right here can now be written as an XY coordinate point. Does that make sense? So rather than calling this an opposite, an adjacent, and a hypotenuse, they're just letters, right? Like we just pick random letters, O, A, right? SOHCAHTOA works because kids remember it. But once you get to like, well, I don't want this to come off rude, but like once you get to like a grown-up higher level of math, rather than saying SOHCAHTOA, we'll just use X, Y, and R instead. Because it's more universally applicable, if that makes sense. Let's try an example here. This is what I had the sub try to do with you guys yesterday. So let me try it again. Now that I've given you a little more background information, and see whether this makes more sense a second time. So first thing I'm going to do, I guess to answer your question maybe about why they're in, the reason why we like X's and Y's now is because if I give you a point, like say 3 and 6, I can plot that on my graph. 3 and 6 goes right there. Right? There's 3 and 6 been plotted. And if I want to make a triangle out of it, it looks like that. Now, if this is where our reference angle or our standard position angle is measured from, normally we would have said this is the opposite, the adjacent, and the hypotenuse. That's not wrong. The grown-up letters now would be to say that this is really your y value, this is really your x value, and this is your radius. As your angle increases, it's like going around the clock, kind of, only you're going backwards. Does that make sense so far? Okay, we plotted point P on a grid. Now I'd like to find the exact values of the primary trig ratios. So let's try all three of them. Sine is normally equal to opposite over hypotenuse. We're now going to say that that's actually y over r. Same thing, like don't do anything different, it's just be aware that we use different letters. So, what's our y value? 6. What's our radius? Actually, I haven't solved for that yet, but do you guys feel like you could by doing Pythagoras' theorem? 3 squared plus 6 squared, 9 plus 36 gives root 45. We're not done yet though. Root 45 can be broken up into 9 by 5, which means you can call this thing 3 root 5. So the exact value of your radius is 3 root 5. We'd like to try to avoid decimal numbers whenever possible. Okay. I mean, if we have absolutely no choice, fine, write out the decimal number. But since we can and have the skills to, let's leave it as an exact number here. So you would say that it's 6 over 3 root 5. 6 and 3 can cancel. You can get yourself 2 over root 5, which means it could be 2 root 5 over 5. Did that make sense? It's a lot of honking. That's fun. Did all those steps there make sense? Yeah. From the top. 6 is literally the y value, the opposite. 3 root 5 was our reduced version of the hypotenuse. I canceled the 6 and the 3, made it a 2, but I had a root 5 on the bottom. So I rationalized the root 5 into root 5 over 5, by basically you times by root 5 over root 5. So what we now can say is that sine of theta is 2 root 5 over 5. So there's one. That's one of my trig ratios. Okay, cosine.
You gotta write them all out?
We're going to write them all out.
Every time?
For practice, yes, right now. Again, if this set, like, because you're giving me a look or a feeling here where you're like, this is dumb, why write them all out? Or is that what you're getting at here?
Yeah.
Yeah. I'm trying to do this knowing what sort of skills you need going forward. Because it seems silly. Why would you write it all 6 times? It's just, I really want you to have a grasp on this for next year when we actually do something with it. So, I know, I'm sorry if this seems dumb, because honestly it is. I hate the way they rearrange the curriculum. Okay, cosine would be adjacent over hypotenuse. So cosine would be the x value over the radius. Your x value was 3 over 3 root 5. 3 over 3 just kind of cancels to give you 1 over root 5. So your final answer then would be root 5 over 5. Slow me down if I'm going too fast. I am kind of skipping the explanation a few steps here. You able to follow that? Okay. So then you'd say that cosine of theta is root 5 over root 5. That's its ratio. Sine and cosine usually suck. Tan, however, is quite nice. Tan has been defined as your opposite over your adjacent, which is y over x. Well, your y value was 6 and your x value was 3. Is that right? So literally your ratio here was 2 over 1, I guess. So you can just leave it as 2. Okay, first thing I want to point out here. Let's say you wanted to find theta. You could use any of those 3 to solve for theta. You could inverse sine 2 root 5 over 5 and get theta. You could inverse cosine root 5 over 5 and get the same theta. And you could inverse tan straight up to number 2 and get the same theta. Does that make sense? So when I ask you in the question here, determine the value of theta using the inverse of the primary trigonometric ratios, I don't care which one you pick. Although I do have a suggestion for you. Go tan. Just because it's easiest. Right? Because tan is usually going to be a whole number over a whole number, whereas your radius is going to be something gross. So, anyways, when you want to find that theta, let's call it 63.4 degrees, give or take.
Do we have to make the theta whole, or whatever it's called?
An exact value?
Yeah.
Not this year. So next year we're going to talk about how to work, well, even tomorrow we're going to talk about radians. Radians is the other unit of measurement for angles. You guys are so conditioned to using degrees. The problem with degrees is it's so hard to get them exact because it has to land like literally on a whole number. So radians is another measure of doing this, and those will be exact, if that makes sense. So starting tomorrow and way more next year, we'll talk about how to do all of this stuff again in the other unit. And then rather than having to round and say it's 63.43, the answer might end up being, you're not going to like this, it might be like 2 pi over 7.
Oh, I can't wait.
And that will be the answer. Yeah. We'll get to that in a bit though. Again, you can maybe kind of see why I don't like the way we phrase this, because you ask a great question, and I have an answer for it, it's just, we have to do it like step by step and build into it, and I feel like it's like a season-ending cliffhanger for like a TV show, where it's like, the answer is now a year and a half away. And you guys okay so far though? Okay, let's do the inverse ones then. Or sorry, the reciprocal ones. If I ask you for the reciprocals, you just flip it upside down. Sine correlates to cosecant. So cosecant basically says flip these upside down. So you know how we used to have 6 over 3 root 5? This is really easy. It's now just 3 root 5 over 6. Which is root 5 over 2. If our calculators had an inverse cosecant button, we could find theta from that. But your calculator doesn't usually make one of those buttons because it's not necessary. You just use this one instead. Okay, cosine has a buddy called secant. Just flip secant upside down. You know how it used to be 3 over 3 root 5? Well, now it's 3 root 5 over 3, which is just straight up root 5. And then tan used to be 6 over 3. Well, I'll flip it upside down, it's 3 over 6 or 1/2. Any one of these things right here, if you inversed them on a calculator, should give you the same angle. Having all of them is completely unnecessary though, right? You just pick one of them. So far so good? Okay. You guys want a quick break? Because I still have more, don't I? Okay, I got 2 more examples like this. Do you guys want to keep going through or do you want to take a break? It's up to you guys. I don't care. Okay, let's just keep going, I guess. Yeah. Okay, so here's the twist now. I'm going to take those same properties I just did, but now we're going to work with angles that may be more than 90 degrees. I'm going to show you where -3, -8 lies. -3, -8 would be down here. See how it goes down there? That's -3, -8. Now it always has to go back to the vertex. That's kind of how we've defined this to work. And it always goes like along the x-axis. So in a way, what we have is an angle that's going all the way around like that. If I ask you for the standard position angle, the standard position angle is going to be like 250 degrees. Does that make sense? The angle that this will have rotated through is going to be much larger than something like that. But in order to get that large angle, this standard position angle, to get that large angle, we're going to have to start by using what's known as that reference angle triangle, which means draw the triangle back to the axis, the x-axis, like this. Okay, when I write out where these fit then, this is actually going backwards 3, and this is going down by 8. See how that works there? And those negative signs are very important because if I didn't use negative 3 and negative 8, positive 3 and positive 8 is up in a different quadrant here. So I do want to make sure that I use the negatives because that indicates that the angle we're going to have is going to be a greater than 180 degree angle. That being said, a lot of the math for this triangle right here works the exact same. So let's try this out again. Same thing we did before. First we need to find the radius, the rotating arm that goes in a circle. To find that, it's going to be 3 squared plus 8 squared. I skip the negatives just because when you square a negative, it doesn't really matter because it'll be positive. So it's 9 plus 64. So this guy right here is root 73. So Jake, a little while ago, you asked why we have to write all 6. I just want you guys to practice it. Not that it accomplishes anything, but the more you do it, the better you'll get, so that next year you'll be like, oh yeah, we've done this before. So let's write out all 6. First one is going to be sine of theta. Sine of theta is the opposite over the hypotenuse, only we're going to change that. It's actually the y value over the radius. What's our y value? Good, don't miss the negative. It's negative 8 over root 73. Only that's not written in what's considered rationalized form, so you'd be expected to take it to this. Negative 8 root 73 over 73. Cosine. Cosine is x over radius. Your x value is negative 3 over root 73, which you'll change to negative 3 root 73 over 73. Sine and cosine suck. Because you're just working with these crazy intense square root values the whole time. And in order for me to foster good skills in you guys, I'm trying to make sure that you do them exact rather than doing decimals. Because I mean, if I let you do decimals, it's way easier, right? Tan, however, tan's the easy one. Tan is your opposite over your adjacent, which is y over x. And what is that? It's negative 8 over negative 3. So that's just 8 over 3. That make sense? Any of those 3 should be able to get you an angle. We'll do that in a second, though. Let's write the other ones out. Sine's buddy is cosecant. Oh, I didn't write that properly. Fix that. Sine's buddy is cosecant. CSC theta. And all you're going to do is flip it upside down. So you know how right here I had negative 8 over 73? Just make it 73 over negative 8. Cosine's buddy is secant. So it was negative 3 over root 73. Just flip it upside down. Make it root 73 over negative 3. And tan's buddy is cotan. It used to be negative 3 over negative 8. Flip it upside down, make it 3 over 8. So far, so good? Last step. We're going to try to calculate that angle. and this is the part that, this is where kids get confused. As bad as it's been so far, this is the part that really drives kids crazy. I'm now going to try this with my calculator, and you know how last time, any which way I solved it, I get the same answer? It's actually not going to happen here. Let me see if I can explain why. First thing I'm going to do is I'm going to try inverse signing negative 8 root 73 over 73. Like I'm inversing this ratio right here. If I do that, I get negative 69. First issue. What the heck? How do I get a negative? Okay. Well, what your calculator does is it calculates the smallest angle that it possibly can. You know how this angle right here was supposed to be like 200 something degrees? Your calculator was able to find an angle that matched the parameters, but it was able to find a smaller angle. It found an angle down here in this quadrant, where you see how it was looking for a negative y value? Well, look, right in this quadrant here is a triangle where you could have had a y value that was negative. And it actually found an angle in this quadrant right here by going backwards by 69 degrees. Now, although that's frustrating, you just have to be smarter than your calculator, and you have to recognize that what it actually calculated was a reference angle for you. This reference angle right here is probably 69 degrees. Well, not probably, it is 69 degrees. Which means that this angle right here is also 69 degrees. So if you want to know all the way around, take 180 degrees, because 180 would get you to here, right? And add 69 more. Now we know our angle. 180 plus 69 degrees means my standard position angle would have been, give or take, 249 degrees. I'm going to prove this to you.
Oh, I believe you.
I'm going to find what negative 8 root 73 divided by 73 is as a decimal number. And I'm now going to find what the sine of 249 degree is. And hopefully, they're roughly the same value there. So one more time. I found what this ratio was right here. And I found what the angle was that I thought fit. And I tried them. And they basically are the same. They're minus the fact that it's not exact. Let me try this a second way. Let's say I tried cosine. If I inverse cosine this value right here, negative 3 root 73 over 73, my calculator spits out an angle of 110 degrees. And the first thought you should have is, there is no way that this angle all the way around here is actually 110 degrees. What your calculator did is it found the lowest possible angle it could that met those parameters. You were looking for something with a negative x value. Now, in this quadrant right here, your x value was negative. But there could have been a triangle in this quadrant right here where your x value is still negative. Can you visualize how there's like a second one that meets those parameters? And because of that, your calculator said that that up to there was 110 degrees. Now, we didn't actually tell you your standard position angle, but if I take that and subtract from 180, right in there, there's my reference angle of 69 degrees, which is what I kind of got the last time around too. So it actually does kind of fit together a little bit. Let me even try the last one here. Let's try inverse tanning 8 over 3. Now I get 69 degrees. Hopefully you'd agree though, 69 degrees would have been if it was in this quadrant right here. Because what your calculator did is it found the lowest angle it could that had a positive 8 over a positive 3. Well, look, here there could have been a positive 8 and a positive 3 right here. So it actually found this guy right here to be 69 degrees. But the reference angle right here is really 69. So once you can figure out what your calculator gave you, you can hopefully work backwards and find the actual standard position angle all the way around the circle. That's the hardest part. And here's what I find frustrating. It's at this point here that they say, and now stop. Where it's like, it would be nice to actually do something more with this. because it all of a sudden gets to like this ridiculous degree of difficulty. And there are actually things that we do in grade 12 that maybe help make this make a little more sense, but we don't get that far. So, how bad was that?
That was really bad.
Just long.
Better than yesterday.
Better than yesterday?
Yeah, way better.
Okay, let me try one more example here while I got time. See whether I can solidify a little bit. Are you guys okay on examples?
Yeah.
You don't want to do an example?
There isn't any
Is there not?
anymore.
Oh, there isn't one more. Okay, can I do one question off your assignment then with you? Can we do number 5? 5? Yeah, can we do number 5A? I'll do 5A with you. Perfect, okay. Okay, so number 5A says find and sketch the 2 reference angles, I think, that are going to make sine of theta equal 1/2. So the first thing you could do is you could kind of plot a graph here, and you could say, well, sine is normally equal to opposite over hypotenuse. That's kind of the traditional way. But our newer definition, our better definition, is that it's y over r. Based on that information, I kind of know whereabouts to plot this. 1/2 means that I would need to have a y value of 1 and an r value of 2. So far, so good? Can you find me the adjacent? What would the x value be? Yes, on the x value? Good, it's root 3. Because it's 2 squared, which is 4, minus 1 squared, which is 1. So this side is root 3. What would this angle be? Well, to find that angle, just do what we kind of always have been doing. If you inverse sine 1 over 2, that should give you your angle of 30 degrees. Or if I inverse cosigned root 3 adjacent over 2 hypotenuse, that should also work. The reason why is that your standard position angle really is your reference angle. But that's actually not the only location on here that's going to give you sine of theta equaling 1/2. There's another location that would work, and this just kind of takes practice. You also could have a triangle right here, where here is a y value of 1. Here is a hypotenuse or radius of 2. See how I kind of have an identical triangle there? This side right here would have been root 3 in terms of its raw value, but because it's going backwards, we'd have to call it negative root 3. That makes sense? There.
Is the radius never negative?
No, good question here. The radius is always considered a positive value. Because even if you think of like a real life scenario, you couldn't have a clock that goes around in a circle with a radius that's like a negative number. But based on its location to the origin, you can have x and y values that are considered negative relative to each other. That's a good question. Okay, well, based on this right here, if this angle right here is 30 degrees, shouldn't that angle right there kind of also be 30 degrees? That's known as a reference angle. So one of your answers is 30 degrees. 30 degrees does work. But there is a second angle that also works. All the way around to there would be 150 degrees. So there's actually 2 answers. And that would get you sine of theta equaling 1/2. Let me show you this in the calculator. If you did sine of 30, it equals 1/2. But if you also did the sine of 150, it also equals 1/2. So what makes this frustrating then is that when you are inverse sining, for example, 0.5, it is going to give you an answer. It may not give you the answer you were expecting. If it gives you an answer of 30 right here, but you're expecting an answer in this quadrant over here, you have to use some common sense and kind of work backwards and figure out what it should be. Make any sense? Yeah, let's try another one. I'll do one that's maybe not on your assignment, but just another one like it. Let's say that I told you that cosine of theta equaled 3 over 5. So here's what you could say. You could say 3 over 5. Well, cosine is equal to your x over your r. It's your adjacent over your hypotenuse.
Is that still a question on that?
I mean, it's like a question 4 or 5, whatever it is. I'm just making up a new one.
Alright.
This is from Zane.
Oh, thank you.
Yeah, you're welcome.
So if I were to plot this, I could have a 5 right there for my radius, and my adjacent could be 3. What would the other side be? Do you guys know this off the top of your head? What 5 and 3, what the other side is? It's a 4. Okay. That is one of the triangles that could work. But I can throw a triangle in a different quadrant that has a ratio of 3 to 5 for cosine. Well, let me try a different location here. What if I put it right here? And I put 5, 4, that would have to make that negative 3. Is that going to work? Well, no, because it's going to have a negative 3, so that doesn't work. What if I put it in this quadrant here, though? This side right here would still be 3. This would have to go down 4 and 5. But wouldn't cosine still have 3 and 5 there? So to answer the question, you would then inverse cosine 3 over 5 and get the reference angle, which let's call it 53 degrees. Well, that's one of the possibilities. The other possibility would be to go all the way around the circle, everything but 53 degrees. So 360 minus 53 means the other angle that works would have been 307. Both of those should work. And then if I try them, if I do the cosine of 53, you know how 3 over 5 is basically 0.6? Minus the fact that I'm rounding poorly. Cosine of 53, that's 0.6. But if I also typed in the cosine of 307, you get a second answer. If there's one parallel between trigonometry and the beginning of the year, remember how when we did quadratics, there was a fundamental shift from there being one answer to there being 2 answers? You kind of have that same thing happening here, where there's actually more than one location that this could work. And so that's my goal, is to kind of get you started on this idea that when you're looking for sine, cosine, and tan, all of what you guys have been doing so far up till today has been in quadrant 1. There is a doppelganger in one of the other quadrants that also could work. And we need to find that second one as well. The downside is now we just stop. We don't go any further than that. So
Doppelganger is funny word. Is it German? It sounds German. Because doppelganger in Dutch is double. And doppelganger sounds German.
okay. Did that make any sort of sense?
Yes.
Okay. It's dumb. I promise you. This will seem to have no purpose. I promise you, we do build on this, but we wait till next year. So hopefully I've done a fairly good job of explaining what's happening. I will get to the why a little bit better when we can piece the whole thing together. So, okay, last slide then, the one I skipped here. Where is it here? I do have kind of a summary slide here to help illustrate how that works here. In quadrant 1.
Excuse the interruption. Sheila standing alone, can you please come to the office for a message? Sheila standing alone, please come to the office for a message.
In quadrant 1, which is the quadrant we've almost always been kind of working in just without talking about it, the reference angle and the standard position angle, it's always nice and straightforward. Everything's usually positive. As you move to the other quadrants, something becomes negative. Here, the x becomes negative. Here, x and y become negative. Here, the y becomes negative. But it means that everyone's got a doppelganger. For example, if I asked you to find me a quadrant where sine of theta equaled negative 2 over 5, you can have, remember how negative 2, that's the y value? I can have a negative y value in this quadrant, and I can have a negative y value in that quadrant there. So when sine is negative 2 over 5, I actually have 2 different answers here. Does that make sense? If I were to ask you where tan of theta equaled 1 over 2, 1 over 2 could go here where they're both positive. Or it could actually go in this quadrant right here where it could have been a -1 and a -2, and both of them could have been negative. There's actually a second quadrant there that fits as well. The key to solving this is that although around the circle to here is the standard position angle, they all have a reference angle. And if you can figure out what the reference angle is, you can work backwards. Okay, I'm done. Thanks for bearing with that, guys. That is a challenging topic. It really is. And it's kind of dumb.